Okay, so we were here, we were calculating histograms together. So we have a that's like this one. And then we have said that a histogram is a count of how many times we have seen a pixel of a given value. So this image is, this particular image is between 0 and 15. So we can identify which are the pixels that have value 0, that have value 1, value 2, so on. The black spots are the ones with those values. And then we may try to understand this background here that is relatively bright is at level 12. That makes sense. And now we have to count how many times we have these values. Value 0, we have 2932. So this is the number of pixels that have this value. And then number 1, 2454, and so on. Okay, so now we have the history. Very good. Then the histogram, we have reason this. So the domain is the gray value, and the range is at most the number of pixels that we have. Number of pixels, the maximum number of pixels is a number of rows times number of columns. Okay, so yeah, what if we have a color image? So if we have a color image, there is no such an operation of counting vectors. So what we can do is either to make a three histograms. So one for red, one for green, one for blue. Or we make so either we make the histograms or we make a histogram that is 3D. Okay, so let's see that. Possibilities. So now we have vectors. And these images are vectors, so we have every pixel, every location. And have a red value that location, green value for that location, and blue value for that location. Then we can construct the histogram. I will refer to the histogram as age. So we can construct the histogram of red, and they are red. I mean, this is discrete because red values can only take discrete values. So, and then the same for the others. Red, green, green, okay, this is one possibility, and these are 1D histograms. They are 1D. What are these? Then you know they are 1D because what are they? Are 1D. Okay, but I can construct something else. Let's remind something from standard extents. So let's say that you have a collection, of XY values. I, Y, I. So you have a collection of XY values. These XY values, they're coming from two random variables. Capital X, capital Y. These are two random variables. And then you can construct things. So one is the joint distribution. Joint distribution. So Y is whatever. Okay, this is the joint probability density function. This is a PDF. Are you familiar with this thing? Yeah. And you can also do something that is compute the margins. So you can margin. This is capital, these are small. So you know the difference. This is the random variable, this is a particular variable, that random variable. So you can compute the margin. The margin over X. I can also compute the margin Y. This margin, that's the integral presence from here in the joint distribution. You integrate. So you are familiar with this kind of thing. So we can do the same here. So we will later say, okay, histograms are approximations to PDFs. This is somehow related to PDF. We have to normalize them, but to be the PDF of R. Then we can construct the join. So business space, more some. Fine. So steps. Say that they have a collection of points. Have a collection of points. The collection of points is defined as two variables, X and Y. Then you can put the marginal of Y with the marginal of X. What we are doing. Okay. But now we are going in 3D. Okay. So you can construct also the histogram, the joint histogram of RGB values. That's used rather than that. Okay, so this is what is explained. This is this plus 1, 1, 2, 3. This is just MATLAB code. Store these things. But the concept is the joint distribution of the values or the marginal distributions. Okay, so let's say that we have this image, and then we can compute the histogram of the red, the green, the blue values, and we already know how to interpret them. And we will introduce something more, that is the histogram of the luminance. So we haven't introduced the luminance yet, but we will do it now. But the luminance is somehow how many depends this image is at each one of the points. So it is more or less how much light you are receiving, no matter what is the color of that of those spots. Yeah, so you can think of as a gray, the luminance is a gray. Okay, so this is not luminance, but almost there. So it is the value. So for instance, let's say that you have a color image like this one, and you don't care about the color. So one possibility to say how bright the image is simply compute the average of the channels. Okay, so at every location, you compute the average. They are in a big channel. And then we will call that the value. This is the luminance. So Y, so if you look at here, So you have mentioned the weighted average of the three channels. And this weighted average, the weight of each one of the channels is 1/3. Yeah. This one is for the Instagram. Class one is because MATLAB, they already is one. Okay. So, yeah, so the weights here are 1/3. And why 1/3? Why we not give different weights? Yeah, we can give different weights. Can be 0.39, 0.6, 0.6, 0.1. Okay, and these weights, these names were the ones that were used in this NTSC system. It was the National Television System Committee. So they got together, but now you have digital TV. But before digital, that was analog. And analog TV. Before the analog TV, for the digital was color TV. But before the color TV, analog, there was monochrome analog. Okay, so but real life is color. So how I encode coloring into something that is monochromatic and doesn't match quality? They were playing a bit with the weights. They discovered that these weights, they are the ones that we like the most as humans. So as humans, we give more importance to green, and then a little bit less importance to red, and blue is the least. And we will see why the next lecture, or in a couple of lectures. Okay, so yeah, this is okay. So here we have an example. So you have color ratings, and then you have the value. The value is just the average rate. So this is the histogram of the value. So that means how many times you have seen a value 0, 1, 2. And the luminance, so instead of the value, the luminance, now you can compute the histogram of the luminance and say that they're similar, but they're not exactly the same. The quality, the perceived quality of the luminance is a little bit better than the ones of the value. Okay, there is an interesting that is the value histogram. So the value is the average of RGB. So we can maybe pose the following question. Pose the following question. So value at a given point is the average. Exactly. Simplification. Average of RGB. And then we can compute the histogram of the value. Okay, and we could do the opposite. We could compute the histogram of R, the histogram B, histogram B. Now we just compute the average of this thing. One level. Are these the same? Or is it the same? Computing the average and then computing the histogram, or computing the histogram and then computing the average. Same. using a pixel tree. It's not. And so the question here is, can put it in terms of system. So you can compute first the average. These are complex vector value sequence. Have an image, it's a vector value, so you can see the average and then compute the histogram. Now what we are wondering is if it is equivalent. First computing the histogram. Then computing the average. So what you are wondering is if these two systems commute. What is the condition for both systems commuting? Or which kind of systems do you know that commute? Linear systems or linear systems? Computing the average is a linear system. It is. Okay, we will see now why this is a linear system. Computing the histogram is a linear system. It's not. So counting is not a linear system. Okay, so what is the definition of a linear system? Okay, let's switch one to find that. So a linear system is one for which we have, so let's say that you have okay, so you have a system. Have an input x, and output y. Then you know that y1 is the output by given input x1. Y2 is the output by given input x2. And then if you excite the system with x1, a x1 plus b. This is a. This is a. Okay, so let's see. Computing the average is a linear system. I will do it with two sequences. Okay, because it is it's more convenient. Okay, so computing the average. So our system is have an entry and it's a vector, and what is it? Y. So y is the average of x1. And let's call it x, the first component, let's call it xa. I mean, x1. Okay, so this is our system. So now we have a couple of entities. Entry A and entry B. This is given by A. This is given by B. This is the average of this. One. The average is A, is B. Example 1. Okay, now we put into the system. We put the system the addition of the two. So put into the system is the average of A is A at B to B 1/2. Then A H A plus B B first component plus A second component. Do you agree? Okay. Now, this is A. It's the first component. First component of that vector is A1 plus B1. Second component of that vector is X plus B1. I can separate that in, I can reorganize that. One part of A, I will put the everything that depends on the, let's say I put it first. So I will get rid of breakfast. So this is X A one A X. That's the one is X. This is A, all these. And take the A out. So all this is A. This is A. This is B. All this is this is what I wanted. So if I excite the system with the weighted average of two signals, what I get is the same weighted average of the two outputs, the two individual outputs. So there is no point. Computing the average is a linear operator, but this is just an exercise to make you familiar with these terms. And the histogram is not. So if you make a weighted average, so you can count the example. So there are any bits. So you can have any bits. So it's you got once. So what is the histogram of this instance? Then the axis should be at the right. Okay, so this is the histogram. This is image one. A stage. Now image B is the same. It has the same J, and image B has the same histogram. And now you construct a new image. C, that is I minus YB. What is the histogram of IC? Over C. So we have a weighted average of the input, and the output is of the weighted average. So computing a histogram is not a linear operator. So these two these two systems do not converge. They're not linear. In general, that there are making this such a strong statement. So I'm sure that there are pairs of non-linear systems that can converge. In general, they don't. Okay. Histogram is not linear. Average is linear. So it shouldn't be the same. So let's see if it is the same process. Yeah. This one. Yeah. So if the making a histogram is linear, then the histogram of C should be the histogram of A minus the histogram of B, but it's zero all the time. But the histogram of C is not zero all the time, it's this one. Okay, so yeah, so histograms are non-linear operators. So they shouldn't be the same. So here we have the RGB histograms, we have the histogram of the value, and here we have these. So we have the histogram of the value. That is this one, the black. And we have in blue, we have the average of the histograms, and they're not the same. They're very far. So just be careful with that. So whenever you have non-linear operators and not linear operators, you can compute. This is one dark code. That. And now it comes this thing of computing, making the histogram, turning the histogram into a go back here. So we have probability density function. So we are now here, our probability density function. So which is the main property of a probability density function? One of the main properties. Any function can be a probability density function. That is a very hard to explain. If I give you, for instance, a Gaussian here. This is a probability function. Mine is our Gaussian. Any Gaussian is a probability density function. That is a very hard to explain. It's that the area has to be one. The area of this one. So the same. Okay, this is the probability density function of a discrete signal, of a continuous signal. So x is continuous. Just continuous. What if my function is not continuous? My variable is not continuous. So I have a discrete variable. Now I have a variable G. The gray value that we know that in our context it goes from 0 to 255. No, that's negative. The probability density function. Set of deltas. And you know there are two kinds of deltas. It is thanks. It is normal to say here capital T. Capital T is the random variable. The small g is the particular value that we are considering. So there are two kinds of deltas. So we have B delta. Say delta A. We have Histograms. Yeah, delta. Like this, we say delta T. What kind of deltas should we use there? Or it doesn't matter. Direct. Yeah. But you should have this kind of delta. So we take value 0, 1, 2, whatever. Goes up to 5. Okay, and we have to put numbers there. So let's say that I put number 0.01. What does it mean? This is a small business. 1. So what is the meaning of 0.01? Is it something? Huh? It is the area under this delta. Okay, that's good. And then what is the area? So what is the meaning of the area in this context? 1. This is the area, but what is the meaning of the area? The context of probability density functions. Is here 0.1 is the probability of the random variable taking the value 1. Good. What about this one? So this one, let's say I have normalized. This is I don't think it's the same value. I don't know what is the Gaussian value. Let's say it is 0.01. It's the mean. And I say the same. So it is the probability of the random variable x taking the value 1. It's like that. This is good. Okay. So the probability, this probability, the probability of any quantum variable taking a particular value is always zero. If the variable is continuous, if the variable is discrete, no, then it's not zero. Can be zero, can be whatever. But for a continuous variable taking a particular value, it is zero. If I want to compute areas, what do I do? You want to compute areas, you have to do an area. The probability of x taking a value 0.995 and 0.05. Okay, I don't know. It's the icon. Okay, so this is a reminder of what probability density functions are. And yeah, here we have the same kind of constraint that we have here. Okay, so here for continuous variables, the area has to be 1. And here for these ones, you also have that the sum over all G's of M of G. This is also that is the constraint on this kind of function. Okay, so now we have our histograms. We have our histograms. This one, for instance. Is the histogram a probability density function? It's not. The sum of all these values. If this is 10,000, so the sum of all these values is 1. So it cannot be a probability density function. But we can tell you the probability density. If I divide by the total number of pixels, that is what is expressed here. If you divide by the total area of the image, the total number of pixels, then it is a probability density function. Now the sum is 1. Something. Yeah. Okay. So now we have divided by the total number of pixels, and now our values, they no longer go 10,000 days of they stay radically smaller. The sum of all these numbers is 1. This should be discussed. Our gray value is discrete, but it is very inconvenient to show that that's what to show kind of continuous plot. But it is just a matter of representation. You know, it's made of letters. And what is the meaning? So this axis, because these are the that's this axis means probability. So what is the probability? This is I don't know, 1%. Okay, this is 1%. So what is 1%? It's a probability that if I take the value at random from this image, I take a random location, anyone, take any location here at random, it's a probability that it has, this is the value PDF. So what is the probability that the value at random is, I don't know, 60, is 1%. That's the meaning. Okay, so if you take a histogram, divide by the total number of pixels, now what you have are probabilities. And it is the probability of taking a pixel at random. It's the probability that it takes that particular gray value. Okay, now we have another guy there that is the CDF. CDF is the cumulative density. It is the cumulative density function. Okay, so let's start from here. So I will make new drawings. So we have a PDF. PDF. X, 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 I don't know, whatever. Can be whatever, but it is a probability density function. So we know that the area is 1. And we have reason that areas are probabilities. Okay, so now I may wonder, okay, what is the probability? So I will look at the particular value. But what is the probability that if I take at random any value from this random variable, it is smaller from X? Is this probability? That's probability. Is this one? Is all the area up to and from. So that is that from minus no, or the probability is not function. And if we the value by the integrate. Okay, so that is all the same. What we are saying here, it's just the same. Okay, and we will follow that. That is another function. If I change x naught, then what I have is another function. We will call it. Okay. Okay. F of x. We are not very creative. And that is the cumulative. Okay, so this one, probability density. And now we understand the word density. Density is a density because to get probability, we have to integrate. That is the property of density. So if you have an object, you want to compute the mass of an object, you have to integrate the density of the object. Okay, so it is a density. And this one, on that density. Okay, it's cumulative, but we are accumulating up to x naught. And now, this one should be, the area is always increasing. So if I move x naught, if I move x naught, then I have is something at the beginning, it is 0. It is 0. It is 0, and then it is always increasing, always. At some moment, here, it doesn't go anymore, it stays flat. What is this flat value? Where does it go? It starts at 0, goes to 1. Okay, so this is the CDA. Okay, so make all these CDA. CDA. And we know how to go. So if we have the PDA, know how to go to the CDA. Yeah, it's the Instagram minus created in layers of PDF. So if you are given the PDF, you can compute the CDF. Okay, that's good. What about the opposite? You are given the CDF and you want to compute the PDF. What do you do? You are here integrating. You have to differentiate. So this is the derivative of PDF. Back to X. Okay, that is for continuous signal or for continuous variable. And now you have the equivalent for random for discrete variables or for discrete variables. So for discrete variables, if you are given a PDF, it is a set of delta. Now CDF sum from say I want for minus and ways all F I and we want to go to the other definition. What is the opposite operation of summing? First difference. Have to do CDF of X minus CDF of X. Perfect. Is this okay? Good. Okay, so these are these slides. All these slides they are saying that. So have to divide by the area. You have, if you want to express the area, this area has to be equal to this one, the histogram, the sum of the histogram for all the array values. This is PDF, CDF, how to go from one to the other. If there is a, it's fine. So this is the expression for going from CDF to PDF. This is continued. This is the expression of the algebra is discrete. Same, how to go from PDF to CDF if you are discrete or continuous. Okay, any question? I think it is a good moment for a break. Okay, so the next point, the next lecture is point processing. So point processing, we so far the first two lectures have been what is a limit and some characterization of data, that is this probabilities. So now we will start changing this. So a point process is just concept is this one. Or the concept is having it in something. You will transform it in another typically of the same size. And this one is a transformation of I. And just like this transformation is very free. It can do anything. Takes an input in and transforms it in any way. But there is a restriction for point processing. That is, this transformation only depends on it. Okay, so it cannot take the neighborhoods. So it's taking this pixel, and with this pixel, it is producing this one. Producing this one. And we will see later some other transformations that can operate on loops. So they can, for instance, they can take all these pixels to produce just one. If this is a group. And the other two are point. But the restriction is that you can do whatever you want with the pixels, but it has to be one-to-one. And as such, with it like this transformation can do anything. So I give you the image, I can do whatever I want with the image. We have the whole information there. Okay, so if you want to be somehow more precise in this question, is that it is such that it is a function of I and the function of no matter what. So these functions are known functions. This is right. So can only take one particular value, only one. Only one. Okay, so this is the same idea, but it works. Have use labels, yes, create transformations one-to-one. And this is some examples of point transformations that we use. And here are some examples. So I take the original images and what we will do is to increase the brightness, and now we understand what it means in terms of histograms. So we are shifting the histogram to the right, or we are shifting the histogram to the left, or we will increase the contrast, and now the contrast we understand. So the contrast is the difference between max minimum and maximum. And we can decrease the contrast, we will do some other transformations, but for the moment, we're going to for the gamma transformation, histogram modification. Okay, so yeah, so this is the equation that defines a point processing. So the pixel at the output can only depend on the pixel in the at the same location. That's a function that takes these pixels, one pixel, and transforms it into elements. Okay, I have to say like this, or and so. Okay, so what about if we have images of one band, three bands? Okay, so here or here. So if it is one band, if it is one band, okay, one band, it is one band, so it is a gray image. So this function has to go to R by. You know, this R is the real number set. It is a lazy way of writing. If your images are represented with 8 bits, you have to go from 0, 1, 55 to 0, 1. Okay, but in general, they can go real to real. Okay, just one bit, just one value. And it can be whatever function you want there. Okay, and this is a parenthesis. The most general way of describing a function, this one, x, is a label. So 0 max to 0. 1 max to, I don't know. I'm happy with real numbers, so -1, 2 max to 3. So you need all the pairs. This is the most general way. And sometimes these tables here, they can be written in a nice form. So sometimes you can write that. This is not the case here, but sometimes you can write that. So if you are used to think of functions in this way, but the best way of thinking of functions is a function is a data. There is a one-to-one. Sometimes these correspondence can be very easily written, but many other times cannot. Okay, this is one band. What if I have 3 bands? If I have 3 bands, I don't know. Oh. So now we have 3 bands. And I know my functions will go from 3 values, so they transform the value into okay, I can do 2 things. So one thing is, okay, each one of the values is independent. So have arbitrary function. So you have a function for the red. Right? Have a function for the red. Another function for the green. Another function. This is a possibility. The other possibility is that I force the 3 functions to be the same. That is a single function. It's a single function. And the same function is applied to the 3 functions. So there are at least 2 possibilities. So this is what is explained. So either apply, if this is for one, and when you have three bands or n bands, you can apply the same function to all of them, or you can apply a different function for each one of the bands. My notation is better. General. And the most general way of thinking of a function is a lookup table. Lookup table is this thing. Give me what is the input, I will tell you what is the output. And sometimes this relationship can be coded in an analytical way. But if it is if there is no analytical expression, I don't care. This is still a function. Okay, so lookup table is the best way of thinking of it. So yeah, you know, all the plus ones in these slides, they relate to starting at one in math. The index is starting at one. So you can make this transformation. So for instance, let's say that your input images have values like 0 to 5, and then you construct your lookup table. Your lookup table tells you that the value 127 has to be substituted by 127, and that the value of 100 has to be substituted by value 90, 55, and 5, whatever. Okay, so you construct this table. 101 by 64, 102 by 68, and so on. And so you give me the input image, I look at what is the gray value, and then I substitute by that. And sometimes you can these lookup tables you can do some nice analytical formula like this one, which is kind of sigmoid functions. This is called the sigmoid function. And the sigmoid this is very interesting. The sigmoid it has three important parameters. First one is the amplitude. The amplitude determines from where to where, what is the maximum value. So it's 255 is 5. And then the other important parameter is this one. This one, 127. This 127 tells you at which point you are halfway. Let's see. So you will go from 0 to 255. Okay, so let's say that x is 127. It is 127. All this is 0. And then exponential of 0 is 1. And then you have 255 divided by 2. So this is the point at which the sigmoid stays halfway between 0 and the maximum. And the other one is this a divided by 32. This a divided by 32 shows the slope. Okay, so at 127, you will always be halfway. But how fast you go, you can go faster or slower from 0 to 55. And then this is controlled by a divided by 30. Okay, so sometimes your table would be nicely described by a function. This is a very important function, the sigmoid. And some other times it is just a table. Okay. So this is a lookup table that can be described by an analytical economy. And then you simply have to sum something. You give me an image, I look at in the lookup table what is the corresponding value, the corresponding value, and put it in the output. You do that for every band. Okay, so yeah, so here we have the example. So let's say that this is our lookup table. And then we have values here. So let's say that I have here value 64. The value 64 has to be substituted by 32. So I will put it in the same place and put the value 32. Okay, and this is how I transform my images. And you do the same for the three panels. Okay, so let's look at some examples. So let's say that this is my input image. I can decompose these three panels. And then I apply three different transformations. So the first transformation, so this would be the green transformation, the blue, and the red. Okay, so let's start with the green. So the green, start with the green here. So I'm inverting the green. See, it's just inverting the inversion. So if the green is low in the input, my green in the output is high. If my green in the is high, my green in the output. Okay, so that means that the standard here, the light is reversed. This was very bright, now it is very dark. And the sky was very dark, now it is very bright. It's bright. Okay, so this is easy to understand. Okay, what about the red? The red is also easy. So the red is, if it is dark, it will stay dark. If it is bright, it stays bright. Then there will be a very sharper transition from dark to light. Okay, so this was the red. So if it was dark, it will stay dark here. But look at this as slow. It's a slope is very small. So that means that all the values from 0 to 50, they are almost substituted by 0, 1, something like that. So it will be that even darker. That is why the background becomes right dark. The same happens in the white values. In the bright values, and all these values from 200 to 250, I am substituted by 252. Everything that was relatively bright will be saturated at one of the brightest ones. This is not this one, the blue one. The blue one is special. So up to the half of the range, it will be made brighter. And from that middle point again, I will reverse it. So this is the outcome. The thunder that was very, very bright, now it is very, very dark. But the background that was dark, now it is brighter. So now we combine these three images into a single one and follow the things. This is what it is. Okay, so from this image, and I recover this one. So let's recover this one. Make it intro. So I have an image I have transformed a function. This function, these are vectors. So this function is also a vector. Now, can I recover the input? Have I lost? So if I cannot recover, that means that this transformation has lost information. If I can recover, having it in this way or having it in this way, I don't care. It's the same information, exactly the same information. I can go from one to the other. Okay, so if it can be inverted, I don't care in which way it is. If it cannot be inverted, I have lost it. Okay, so let's look at the green. Given the new green channel, can you recover the first one? we say that my new green channel is 5 times. If I give you this, you can compute the new. If I give you the new, can you recover the old? Yeah. You have to solve it. I can recover. So this is f of t. This is f minus 1. And you have the two spaces. You can go from G, you can do G prime F. You are given G prime and go back G F minus 1. Okay, so that's good. So the green I can recover. So the green is the information is the same in both. What about the red one? I give you the new red and you recover the old red. Almost. Why almost? Because there are values. Saturated values I cannot recover. So if the new red is 255, I don't know which one of these values the old red was. All of them they give. They go back to the path. And what about the blue one? I recover. I cannot. So if the new blue is 150, I don't know if the original was this one, or the original was this one. Okay. And that goes back to very old mathematics for you. That is, remember drawing functions like this. But drawing functions elements here, we're saying, okay, I have a function that transforms this into that, the same function transforms this into this into this, into this into this. So can I, does it exist? F minus 1, but that's if you give me x, I can compute y. You give me y, I can compute x. And this type of functions they were called one to one function. Benefit is PJP. So these one-to-one functions they can be inverted. Okay, what about this one? I have this function here. Another function. But now my function is 4. Will it be inverted? Okay, kind of inverted. So this part can be inverted, but this part cannot. So if you give me this one, I don't know which one it was. This is called many one. What about this function? Function. This one. Same point. What that? Can it be inverted? Yes. This is not even a function. This is not a function. Why is not a function? What is it violating that doesn't make it a function? For the same input, it has two outputs. This is not a function. Okay, so a function for a single input has a single output, whatever that is, whatever, but 1 to 1. So 1 here, 1 here. Otherwise, it is not a function. Very old manipulation. Okay, so this is not invertible, this is not invertible, this is invertible. So we have lost information. Cannot recover the limit. Okay, good. So now, these things we know, so we have an image, the luminance system, and now we will define our transformation like this. So our first operator is will be this increased brightness. So increased brightness is this is the identity transformation, so it doesn't change it. Anything. So we will shift the identity up. Okay, so we will add something. I will add a constant G. We will add a constant G. And because I'm adding something, so 0 goes to T, 1 goes to T plus 1, 2 goes to T plus 2. But my images are represented with 8 bits. So what happens when I'm reaching the end? 255 plus E is larger than 255. So I have to saturate. So all these values is saturated by 5. And this is expressed here. So you have a value, you add T. Again, here you have to be careful with the notation. This is a vector. So vector class scalar is defined. Okay, so we are doing the same calculation in all the 3 bands. Okay, so E, when I add, I'm not overcoming my limit, and I simply add. If I'm going further my limit, and yeah, then if you want to be besides, this should be a vector. So this is a little bit loose, but you get it. And when you write it in an exam, write it. So is this invertible? Have I lost information? I have all these values. You tell me that the output is 255. I don't know what the input was. I have lost information. And this is the effect. Okay. So you have the original image. I increase everything by D. Becomes brighter. Sure. Histogram moves to the right. And there is some saturation here. All these values they become saturated. Okay, so what else? We can do the opposite. We can, instead of adding T, I can subtract it. I have to get to the gain with the limits. And now there is a saturation at 0. Okay, 0. Now everything becomes darker. Shifting the histogram then down to the dark area. And instead of adding or subtracting something, I will multiply by a constant. This constant is K, that is a number between 0 and 1. So I'm multiplying by a constant. But we have to be careful when we multiply by a constant, because so my basic transformation is this one. This is whatever, more or less whatever. This input, this is output, and then this is identity, and then what I want to do is something like this. Okay, this is what I want to do. But yeah, so this is basically a line that goes to that point. So I can shift my axis there. X prime, Y prime. The X prime, Y prime domain, the transformation is very easy. So the transformation is Y prime. And then I have to undo the transformation. Okay, so what is the transformation? If I want to shift to this point, I want to shift to that point. That is X naught, Y naught. Then what is my change of variables? The variables is I prime is I prime is epsilon. X prime is X minus epsilon. But now I have shifted my origin there. Then I do my transformation. First, this is second. And now I have to undo my transformation. I will undo it here. Okay, I don't know. I don't know. That's simply something. Now I have to undo the transformation. Undo the transformation. As we say, Y A X can rearrange case this way. Can rearrange the types of collapse and failure. So this trick for changing the origin is very common, very common. And you recognize it. Let's use a different form. You recognize it. Have this structure. Everything that has that structure is a change of origin. And you also recognize it here. So that is what they have done. So you see this structure. Your variable minus a constant, then the same constant. I have done it more general. For me, this constant could be different. They can also be the same. I have made it different. So, but you recognize these structures. First, you move the origin, then you make the transformation, and then you undo. Yeah, so what about this one? Have we lost information? If we apply that transformation, we have decreased the contrast, but have we lost information? General, no. So if we can represent real numbers, no. If you cannot represent real numbers, yes. Let's say an example. Let's say that that's my input. So I start my transformation will be just to make it simple. Okay, half of X. I've made S to 0 and D to the half. So 0 goes to 0, 1 goes to half drop. Goes to 1, 3 goes to 1, 4 goes to 5 goes. So if you tell me that the output is 1, the input was 2 or 3. It's not a terrible loss of information. And two values are pretty close to each other. Even if you make a mistake, it is not terrible. But I have lost information. So it is one of these drawings. Two values are going to the same output value. So I can handle it. If you are limited to integer numbers, if I'm not limited, let's say that I can represent real numbers, but very, very high precision. So this will be 0, this will be 1, this will be 2, like that. So now it can be inverted. So depending what is your representation, you are inclusive information. Okay, this is decreased contrast. Why are we decreasing the contrast? So contrast is the difference between minimum and maximum. Why this transformation is decreasing? Say that your minimum and maximum are here. Now your minimum and maximum will be here. This distance is smaller than this one. So we are decreasing the contrast. The difference between minimum and maximum now is smaller. Okay, now we will do the opposite. So A will be larger than 1. A is larger than 1. The transformation is the same. You have to be careful with the limits and saturating properly. So now we are saturating. And we know we lose contrast, we lose information. And what about this one? Are we increasing or decreasing the contrast? Increasing, because this distance here, now it is much better. We are increasing the contrast. And now we recognize a pattern. If this is the slope, right? So A is the slope of this transformation. If A is larger than 1, A is larger than 1, we increase the contrast. If A is smaller than 1, we are decreasing it. So depending on the slope, we are increasing or decreasing the contrast. You can do this transformation, we already know. So you take the minimum and maximum of the equilibrium, and you transform it into something else, maximum and minimum that you want. And you recognize the same kind of structure here. So let's transformation goes this one. Transformation goes. A is the new one. A is the minimum that we want. That's maximum. Minimum that we want. Maximum. Minimum times. And you recognize the same kind of structure. J minus J. I. And this is your change by A. This is the change of the origin. You change your origin, you do the transformation, then you are doing. So now, will we increase or decrease the contrast? Depends on what is this value. This value is larger than 1. Then we are increasing. It is smaller than 1. We are decreasing. So this operation is called contrast stretching. We understand. Okay, so you take the minimum, maximum, and the minimum typically you move it to 0, the maximum you move it to 255. And then you are increasing the contrast here. Okay, so have we lost information? Okay, so let's try to track a few images. So let's say that we have this original image. This is the histogram of the value, the luminance, or whatever it was. We don't care which one that is. So let's say this is the value. Okay, so now we decrease the contrast by a factor of 2. So this is again compressing the histogram towards the middle. Now I increase the contrast by factor 2. Okay, so I increase the contrast. This one, I increase it by factor 2. So in principle, it should be similar to this one, but it is not. Why not? That kind of pose. Why do we have pose? So we have a value, then 0, then another value, then 0, another value. This is stable. So let's say let's do a table again. Okay, put again. X f of x that means at 0, 0, 1 as well. 0, 1, 2, 3. Now I have 0, 0, 1. So on. And so this is my forward transformation. This is the increased contrast. And now I want to undo it. So I want to avoid f minus 1 x. Now I try to increase them because again, I over the first one. So I have divided by 2. Now I multiply by 2. But now my values would be 0, 0. There is no 1. So there is no 1. There is a whole 1. And this is the sequence. And here it is the opposite. Okay, so you take the original, you expand by factor 2. So now you move back to saturate the law. So now you decrease by a factor and a half. Now you discover the same. Now there are no holes. Now you understand these holes. And you understand these new saturations. So originally there was no saturation here. But here because of the expansion. I have to saturate. And when I come back, they are saturated. Then you can compute all kinds of differences and so on. So you can have, for instance, this is the original, this is the original at the time, and now this is the reduced contrast restore, high contrast restore, it's high contrast, can compute the difference between low contrast and original. So from these two differences, which one would you say is a worse transformation? So the process is conceptually simple. So I decrease the contrast, and I expand it. Then it is the opposite. I expand the contrast and then I decrease it. So originally, they don't look so technically different. They don't look so terribly different from the original, but these are the differences. Which one has lost more information? Second has lost a lot of image information. The first one, okay, that is just not, is this approximation from 0 to 1, 1 or 2 or whatever, I don't know which one it was. But the differences are random. But here the differences are not random. They have lost a lot of information. Look at this window. I cannot see the window. The history image. They are all lost. Looking only at this one, For me, it is clear, this is lost. I cannot see the details here. Okay, the details here are not perfect, and that is not. They are almost the same. This one, this is the difference between restored and original. Okay, so here you have a lot of structural information. Here is sections. Okay, so let's stop here. Yeah, the test.